Hi and welcome. My name is Keizo Matsubara, and this is the first talk of two in a little mini course called Quantum Gravity and the Nature of Space and Time. And this talk is intended for a general audience of philosophers, and not specifically to philosophers of physics. Hence, it will be a rather non-technical talk. I don't expect much in terms of physics background. On the other hand, I do expect a little bit of background in terms of philosophical terminology and concepts. And even though this will be a non-technical talk, there will be some technicalities that will be mentioned, and especially in the next talk, the follow-up talk to this one will be a little bit more technical. Hopefully it will still be easy to follow for a large audience. And of course, when talking about this, only a very selective presentation can be given. I cannot do anything more than mention a few ideas and bring them up. And given that it will be, as I said, a rather non-technical, we can't delve very deep. The intention is mostly to just introduce a number of ideas and concepts from philosophy of quantum gravity. So, briefly, what is quantum gravity and what is the current scientific status of it? There is no generally accepted theory. So all of this is very tentative. It's not part of established science in the same way as well, the theory itself is not established science. And here we'll talk a bit about philosophical questions about that as well. But the problem is that there is a lack of empirical evidence, and it's very difficult to make direct tests. Very high energies are required to do that. So that's kind of unfortunate. Hopefully there will be some way of testing a future theory, perhaps indirectly in the future. But right now it's we don't know for sure where this will bring us. So once again, this will be a tentative presentation, but it will be based on serious contemporary approaches to develop the theory of quantum gravity. And what is then the challenge of formulating a theory of quantum gravity? And what makes an approach serious? What did I mean by that? And it's important to know then that to have any chance of making progress in quantum gravity, one must know what we've already established or learned in science, in quantum physics and the theories of relativity. And we have to take that into account. The problem is that the theories as they are now, the quantum physics on the one hand and the relativity theory on the other hand, especially general theory of relativity that describes gravity, that's kind of the main issue here. They don't fit together. They don't fit together into one consistent framework. And if we try to deal with situations where both quantum effects and general relativity becomes relevant, it just doesn't work. And we don't know what happens in these situations. So trying to understand things like the early stages of Big Bang or to fully understand black holes, we need a theory of quantum gravity. So that's kind of the challenge. And we need to find this kind of way of combining them, a new theoretical framework that might require modifications to what we know from the previous theories. And why do we need it, the theory? I've already started to address that. It is because we need to combine these very different theories. But let's just briefly discuss those theories a bit. Because what happened in the early 20th century was that our physical worldview was radically and dramatically changed by quantum physics and relativity. So the relativity theories, the special and the general theory of relativity, changed our views of space and time. And as you've probably heard in general relativity, gravitation is described in terms of the curvature of space-time. On the other hand, quantum physics is very different from that, dealing with particles and elementary particles and the microscopic aspects of the world. And arguably, that led to even more radical changes. On the other hand, not specifically dealing so much with space and time. And as I've already said, the problem is that although both quantum physics and relativity have been immensely successful, they don't fit together. And trying to fit them together in a way which we kind of understand that we need to do, because otherwise we will not be able to understand those microscopic scales of space-time. We will not be understanding space-time at its more kind of extreme situations. And that then it's natural to kind of expect that there will be further new changes to our understanding of space and time. It's like the lessons we've learned from quantum physics somehow will affect also our understanding of space and time in a new way. Exactly how that will play out, we don't know, of course, yet. And while quantum gravity in itself is speculative and tentative, and there are a lot of competing approaches working on this, it's very important to know that the quantum physics and the theories of relativity are extremely well supported. And it's still debated how to understand those theories in some respects. Especially quantum physics is still kind of a widely debated area, precisely how we should understand it. What is not under question, though, is its relevance and its kind of importance, because there are so many current established technology that is already based on that, and there's so many experimental results that have been tested. So we know we have to take it seriously, even though it is still kind of a problem to fully understand it. There are some debates about relativity as well, but I would say that there is kind of less of we have more of a clear understanding of relativity compared to quantum physics, even though, as I said, there are still issues there as well. A word of warning, though, even though, as I've said, the theories are empirically established, they are important, and we need to respect what we know from them, even though it's difficult to interpret them. It should also be recognized given that they are difficult to understand, there is a lot of weird and nonsensical things written about that as well. So for a person with little background in physics, it might be difficult to discern what I would say kind of serious discussions on these issues from less serious ones, which tend to just pick and choose cool sounding and crazy ideas from competing ways of trying to understand quantum physics in a non-coherent and clear way. And that can lead to what I would say very non-serious things. I'm just word of warning for that, and it might be difficult to know for a layman how to distinguish the serious from the non-serious, but just a word of warning there. Contemporary physics acknowledges four fundamental forces: gravity, electromagnetism, and the weak and the strong nuclear force. And all of these four forces, except gravity, is described in terms of quantum physics. More specifically, they are described in terms of quantum field theory, which is kind of a more complicated and developed kind of quantum theory. And this is used to describe particle physics. And you've probably heard about the standard model of particle physics. Quantum field theory is the theoretical language used to express that. And on the other hand, as mentioned, gravity is instead described in general relativity in terms of curvature of space-time. And that is not at all how quantum field theory describes things. And I will not exactly go in and discuss how quantum field theory describes it, but it's kind of more in terms of interactions of particles that mediate forces and stuff like that, very loosely describe them. And we need to, for the reasons I've already mentioned, develop a theory of quantum gravity and merge these together in an important way. And without the experimental results that we have, the best we can do now, of course, everyone would be very happy if there was relevant experiments that we could use, but the best we can do now is trying to find a framework that is consistent with all the experimental results we know from quantum physics and general relativity, and fit it together in a coherent and consistent way. And just these purely theoretical considerations makes it very hard. We cannot just dream up anything. Often when you try to do something that would make sense, it just collapses immediately. So even though there are a number of competing approaches, it's quite difficult to even get started in this. And hopefully, in the future, we will find a successful theory that we can eventually test and so forth. And it should be mentioned, even though we in this case are further removed from experimental feedback than we've been before, it's quite common in theoretical physics that the theoretical ideas come way before the actual experimental tests. Just think about something like the Higgs particle that was suggested in the 60s. And that was quite recently, just a few years ago, found in CERN. So hopefully there will be something similar with quantum gravity, but one should also be kind of honest about kind of a more pessimistic outcome, that it might turn out that we will not be able to test that. That will, of course, be bad. I will also now mention a few comments on metaphysics. And I bring this up because this is a talk directed to philosophers. And the main reason I bring this up is to kind of facilitate communications with physicists if you want to kind of go into this field. So in philosophy, especially contemporary analytic philosophy, kind of what we understand of as metaphysics is basically any attempt to describe reality at its fundamental level, or it doesn't even have to be at the fundamental level, just kind of description of reality. Any kind of attempt of that would be considered metaphysical, regardless of what it is based on. So in that sense, if one bases one's metaphysics on science and has a realistic understanding of science in the terms of scientific realism, thinking that the scientific theorist gives an at least approximately correct description of reality, if one has that attitude, which most scientists and physicists have, still in varying degrees, there are kind of different levels of that, one is actually making metaphysical claims. On the other hand, you should be aware that many physicists would not like the term metaphysics to be used. This can lead to some kind of disconnect. And I think this is, to a large extent, due to the lingering influence of logical positivists. So the problem is that in physics, kind of the negative attitude of metaphysics and the idea that metaphysics is more or less the same as pseudoscience or something like that has kind of stayed, even though they are otherwise not at all like the logical positivist, if they ever were, so to say. So just bear that in mind a little bit, and maybe avoid to use the term or explain the way you talk about it. Because, of course, when metaphysics is defined in this broad sense, including both things that are based on science, if we think of them realistically, all other kind of non-science based accounts of realities are also metaphysics. But that is kind of the problem, is that people think of metaphysics as dividing science on the one hand from other things on the other hand, while using this terminology is just different views on metaphysics. This was just kind of a setup, and the reason why I mentioned that is when I'm talking about the nature of space and time, trying to understand how the world is based on this. This is, of course, a metaphysical project. We're trying to figure out the way space-time is, how it works at a deeper level. And quantum gravity may change our views on space and time. And as has already been mentioned, there are many different approaches to quantum gravity. String theory is probably the most popular among physicists and quite famous. Another one is loop quantum gravity. I will also briefly say a few words about causal set theory, but there are many other approaches besides these. And different approaches may lead to alternative conclusions about how to think about space and time. But it's interesting to look and see if there are commonalities and similar things that appear in many different approaches. And it's also another challenge that is very important to address is to figure out how the quantum gravity theory that we suggest can kind of reproduce the space-time picture we are familiar with from general relativity, kind of explain the success of our older theory. So one very main question that has that can be addressed is whether space-time is fundamental or emergent. And many different approaches kind of suggest that space-time might be emergent in some sense. It might be at the more underlying, deeper description of the quantum gravity theory. We might not have space and time in the way we are familiar with. Still, we have to figure out how such a theory can kind of reproduce our kind of level of description that we apply now. Like our old theories must be kind of appearing there. And it should also be mentioned for philosophers from other field that the term emergent here is used in a rather weak sense. It's not meant to be in a strict contradiction to reduction or anything like that. It is mostly that if something is emergent, it's not part of the deeper or more fundamental picture. And it is not supposed to be in this contradiction to reduction. So that's a comment on side comment on that. So just say a little bit about three different approaches, and I will start with causal set theory. And a central part of causal set theory is that it abandons the continuum picture of space-time, and it doesn't have kind of a spatiotemporal description at its as its starting point. Instead, it is a number of discrete elements that form a partial order, and different kind of networks or sets connected with these kind of little connected in this way can form something that approximates and describes reasonably well, even though in a discrete picture, the kind of spacetimes we're familiar with from general relativity. On the other hand, not all solutions behave in such a way that we would think of them as spatiotemporal. They might be kind of more weird looking and not spatiotemporal. So in that sense, you can think of space-time as only emerging in certain specific nice solutions of causal set theory. So that is kind of a situation where space-time as we kind of know it can appear in some solutions but not in others. It should also be mentioned though that causal set theory is kind of more of a starting point of theory to towards quantum gravity. There are a lot of quantum parts of that hasn't really been developed. Right now it is kind of a starting idea that is mostly formulated at the classical level, and we know more about that, but to kind of make a quantum version of that, there's a lot of questions still to answer there. I now go to another a bit more highly developed or advanced approach, which is loop quantum gravity. And there are a number of closely related approaches, for instance, spin foams and others that can be seen as kind of part of the same research program or something like that. And in this case, we also have kind of a discrete picture of space-time arising. But a difference between causal set theory and loop quantum gravity is that this discreteness is not kind of put in by hand from the beginning. It is instead something that we can derive based on other assumptions. That might not tell you too much, but still there is this kind of difference. And also in this situation, we have a large number of different solutions, different so-called spin networks that we should think of as forming space-time or develop into space-time in various ways. We shouldn't think of them as being in space-time, They are supposed to actually form space-time. And when I'm talking about space-time, and the way I describe it now might perhaps fit better in the spin foam description that kind of describes the whole thing as not just individual spin networks developing in time, but kind of more of a total picture. But that might unfortunately not tell you that much, but just bear that in mind. The point, though, the more important point is that even in this case, we need to figure out a way for the different spin foams or spin networks or to represent what we know of a traditional spacetime. And a problem for the loop quantum gravity approach has been to find the more conventional, traditional spacetimes we are aware of. One hasn't even succeeded in describing Minkowski spacetime, which is basically the flat, simplest kind of spacetime. So that's a challenge that they will hopefully overcome. But that is that. I will now go to discuss string theory a bit. And as mentioned, this is the most popular approach among physicists. It also happens to be the one approach that I think I know most about and have worked most on. That should not be seen as me kind of endorsing this versus the other approaches, but I might have a little bit more to say about that, but that more reflects my own background than anything else. The basic assumption in string theory is to replace particles with strings. And these strings are supposed to move through space-time. And at first glance, it seems to be that space-time is more traditional in this picture compared to causal set theory and loop quantum gravity in terms of this discreteness versus continuity, or whether it's fundamental or not. But all of this is a little bit more subtle and complicated. And one will actually see that space-time in string theory and how that looks how one should think about that is a bit more complicated than one can think. But that will be addressed in the next talk and not in more detail, and not here. But there happens there's other weird things that happen with string theory. There will be extra dimensions. And for the superstrings, which are the ones we kind of find most interesting as potential candidates of representing our world, that needs to be 10-dimensional. Once again, that kind of 10-dimensionality and how to think of that conceptually will be addressed in more detail in the next talk. But that is what is commonly said, that you have extra dimensions in spacetime. And string theory seems to be able to combine all forces in a unified picture. And one little nice analogy that is often used is to describe the strings as in such a way that different vibrations of the string correspond to different particles. It's almost like the particles are different notes, musical notes played by the same string. And another thing to extend this kind of comparison or analogy is that these extra dimensions, if we, for now at least, talk of them like that, describe the kind of resonance box or the musical instrument on which the strings are attached. So in that sense, different kind of tones are allowed in different backgrounds, in different ways of kind of forming these extra dimensions. And there are also some other things like that can, D-branes that can be described as things that the strings can get stuck on, and that would be corresponding to like places where we can peg on the string in like different ways and kind of allowing for different notes. But regardless, since we don't see any extra dimensions, they need to be hidden in some way. And they can be compactified and be very, very small, for instance, or there can be some other mechanisms. And of course, many people will say these kind of extra dimensions and all that seems pretty crazy, but still many people take it very seriously because it seems to solve other problems. And this ends this first talk, where I've just very briefly described the problem, different approaches, different questions, and that. And in the next talk, I will discuss a little bit more specifically about space-time in string theory and all these kind of subtleties that I hinted at the end of this talk. And I will also talk a little bit about the problem of time in quantum gravity. Thank you very much.